Before we can really get into risk measurement, we need to spend some time focusing on a review of statistics. Modern financial analysis makes extensive use of statistical concepts and methodologies. So the purpose of this lecture, as well as the next lecture, is really just to refresh some of those key statistical concepts. I broke this out into two parts. In this module, Module 2, we'll focus on univariate analysis, which is concerned with just a single random variable. In the next module, Module 3, we'll look at multivariate analysis, which is really more concerned with the relationships between different random variables. So here we focus on univariate analysis, and we'll look at some of the basic concepts that you're probably familiar with from way back when, perhaps, but we're looking at random variables and data sets, as well as PDFs, probability distribution functions, and CDFs, cumulative probability distributions. There's also the measures of central tendency, mean, median, mode, as well as the measures of dispersion, the range, the average absolute deviation, the variance, and of course the standard deviation. We'll look at moments, we'll look at some other distributions like log normal distributions, and we'll talk a little bit about how you work with continuous versus discrete returns. So what's a random variable? Well, technically a random variable is anything that will take on a numeric value at some point in the future, where right now the precise value of that random variable is not known. We can also know the probabilities associated with the different values that the random variable can take on. So for example, throwing a die, or the value of a stock 1 year from today. We should distinguish between a random variable and a number. Once the random variable takes on a numeric value, it's no longer a random variable. At that point, it's a number, and we would call that an outcome or an observation. The analysis of some random variables require data sets, and the analysis of other random variables don't require data sets. Statistical methodologies are applied to data sets. Data sets are just a set of observations on one or more random variables. Data sets can be of two types: cross-sectional, which are observations made at the same point in time. So for example, if you looked at a random sample of the net worth of 1,000 JP Morgan Chase clients on a particular day, that would be cross-sectional. There's also time series data, which are observations made on the same variable at different points in time. For example, what's the net worth of a particular client at the end of each of 12 calendar quarters? So first, looking at the simplest type of random variable, a die, right? Consider a die just 1/2 of a pair of dice. If I throw a die, there are 6 possible numeric values that could result, and each of these values has an associated probability. As the die is rolling in the air, it's a random variable. Once it stops, it becomes an outcome, a number. Assuming that the die is fair, what are the values that this random variable might take on, and what are the associated probabilities? How can we depict this? Well, we can depict it on a probability distribution, where you can see each of the possible numeric outcomes, 1, 2, 3, 4, 5, and 6, these are our values, and each of these has an associated probability, which is just 1/6. 1/6, 1/6, 1/6, 1/6, 1/6, 1/6. So this complete set of values that the random variable might take on, together with their associated probabilities, is a probability distribution, or a PDF, probability density function. A cumulative probability distribution, or CDF, cumulative distribution function, is the probability that the value of a random variable will lie at or below each point. So you can see it's growing over time, right? We have 1/6 for the value of 1, but then for the value of 2 or less than 2, we have a cumulative probability of 2/6. For the value of 3, we have a cumulative probability of 3/6, 1/2. and so on. The measures of central tendency are intended to find the center of a distribution in some sense. Of course, there are three commonly used measures of central tendency: the mean, the median, and the mode. So if we have this sample of observations, a data set, on a random variable, right, such as throwing a die, we then arrange these in order from lowest to highest. We can then isolate the median, which locates the point such that the same number of observations lie above it as below it. So here this 4 is the median. We have 4 observations below that and 4 observations above it. The mode locates the value that occurs most often. In this case, it happens to be 5. We have 3 5s, and that's occurring the most often. Of course, the most important measure of central tendency is the mean. This is just a simple arithmetic mean and average. The mean is a measure of the center of a distribution in the sense that it is the sum of the possible outcomes weighted by their respective probabilities. We also refer to this mean as an expected value, or it's called the first moment of the distribution. How do we calculate the mean? Well, that depends on whether or not we know the true probabilities associated with the values that the random variable might take on. In the case of the die, if I tell you that it's fair, I'm telling you that the probability associated with each individual outcome is 1/6. But it's also possible that I don't know if the die is fair. Certain outcomes might have a higher probability and others might have a lower probability. If we do know the true probabilities, then we would be calculating what's known as the population mean. So for example here, if we have a random variable x and the different values of the random variable might be x sub I here, right, x sub I. Suppose that there are n possible values. If we know the true probabilities associated with the values, then we can calculate the true mean with this Greek letter mu. And so we would simply be taking each outcome multiplied by its probability and then summing that up from I equals 1 to n. So in the case of the die, we have the outcome of 1 times a probability of 1/6 plus the outcome of 2 times the probability of 1/6 plus the outcome of 3 times 1/6 plus the outcome of 4 times 1/6 plus the outcome of 5 times 1/6 plus the outcome of 6 times 1/6 gives us a mean of 3.5. If you don't know the true probabilities, we would have to formulate an estimate by conducting an experiment, and we would call this a sample mean, which I'm denoting here by lowercase u. The estimation process can also generate estimates of the probabilities of each possible outcome. So for example, you can roll the die t times, right, t times here, and each roll would generate a sample observation or outcome. And we would denote that outcome here with the letter capital O sub I. So the sample mean, you would repeat this process, adding them all together and dividing by t number of observations. Suppose we toss the die 600 times. We count the number of times each of the 6 possible outcomes occurred, and we plot them. This is a histogram. So we roll a 1 103 times, we roll a 2 106 times, we roll a 3 90 times, we roll a 4 102 times, we roll a 5 95 times, we roll a 6 104 times. We've plotted this on our histogram, and then we can estimate the probabilities of each of those 6 possible outcomes. The estimated probability of getting a 1 is 103 over 600 total rolls. The estimated probability of getting a 2 is 106th 106 out of 600. A 3 is 90 over 600, and so on. Well, are these probability estimates accurate? Well, I don't know. How can we make them more accurate? By rolling the die many more times. Of course, the more times you roll, the more accurate your probability estimates should get. So here you can see that you can get the sample mean by adding up all the outcomes and dividing by 600. Or we can multiply each of the 6 possible outcomes by their associated estimates on their probabilities. Either way, we end up with, in this case, 3.49, roughly. Suppose we have another set of observations from throwing a die, and we obtain a sample mean that's very close to 3.5. In fact, let's suppose it's exactly 3.5. Can we conclude that the die is fair from that alone? No, you have to be careful. You could end up with something like this. 300 times you roll a 1 and 300 times you roll a 6. If you were to figure out the sample mean on that, you would get 3.5. But clearly, the die is not fair in this case. So the mean is a measure of central tendency. It's measuring the probability-weighted center of the distribution. But there are also measures of dispersion. Dispersion is referring to the distance from the center that any given outcome is likely to be. We look at the simplest first. That's the range. This is simply the difference between the highest and lowest value. For example, if you're looking at stock prices, you could look at the daily high-low range for a stock price. Next, we look at the average absolute deviation. Here we're looking at the sum of the observation minus the population mean, and then divide that total by n number of observations. A more important measure of dispersion associated with a probability distribution is the variance. The variance and a related measure called the standard deviation have lots of applications in finance. To calculate a variance depends on whether we know the true probabilities associated with the outcomes. If we do, we can calculate the true variance or the population variance. This is known as the second moment of the distribution. If we know the true probabilities, we can calculate the variance using this formula here. So x denotes the random variable, and you'd subtract from that random variable the mean here, which we would have already calculated. So you take the observation minus the mean, square it, then you multiply by the probability of that outcome. You do this over and over for each potential outcome, and you sum it up, and that gives you your variance. So here's an example. Imagine you have a fair die. Of course, it's a fair die, so there are 6 possible values. Each one has a probability of 1/6. The way to calculate the variance on this is just to take that first outcome, 1, minus the mean, 3.5, square it, multiply by 1/6 probability, plus the next outcome, 2, minus the mean, squared, times 1/6 probability, plus the next outcome is 3, minus 3.5 squared, times 1/6, plus 4 minus 3.5 squared, times 1/6, plus 5 minus 3.5 squared, times 1/6, plus 6 minus 3.5 squared, times 1/6. Gives us a variance of 2.91667. Let's take a look at how we might do something like this in Excel. If we had a die with 6 possible outcomes, we could calculate the variance on this. We'd have to figure out the average, or mean, on these values. And we'd also have to know what the probabilities are associated with each of these. So it's really just going to be 1/6 for each of these. And so what we could do then to figure out the variance would be, we said we have to take the observation minus the mean, square it, and multiply it by the probability. We would do this for each, so I'll copy this down, and then I would sum it up. So this is our variance. Right? Luckily for us, though, there's actually a built-in Excel function that doesn't require us to have to figure out all of these pieces of information. So instead, we could just have our observations here, or have our outcomes, and simply use the var.p, variance based on a true population. If we use that, we can just select all of the values here, and you'll see we get the same result. So that was useful when we knew the true probabilities. However, with most financial data, most if not all financial data, it's sample data. We don't know the true probabilities. So instead, we have to calculate an estimate by conducting an experiment. And then when we estimate the variance, we call it a sample variance. So the way this works, it's actually quite similar to what we did before, except instead of dividing by t, we divide by t minus 1 because there is 1 degree of freedom that's lost. The idea is that the same data was used to calculate the mean, which then feeds back into the calculation of the variance. So let's see if we can do this using Excel again. Going back to the data that we had, this was the variance on a true population. But what if it were a sample? Which is more often what we would see. We can use the var.s or simply the var function. And this works when the estimates are based on a sample. So we simply select our observations, and we see that the variance for the sample data is 3.5. Alternatively, if you wanted to calculate this manually, you would be doing it a little differently. You'd have to look at the observations that you had. So let's just say we had these observations. We would have to take the observation minus the mean, 3.5, square it, raising this to 2, and I would do that for each of these. So I would copy this down, and then what I would do is sum these up and divide by t minus 1. So if we had 6 observations, we'd be taking 6 minus 1 degree of freedom, so it would be divided by 5, which would get us to that same 3.5 sample variance that we had before. So here's another example. Here we have a die that we don't know whether it's fair or not. If you toss the die 600 times, just like we did before, from those 600 outcomes you calculate the sample mean, let's say it's 3.49, and then you use that sample mean to help get to the sample variance. You'd have a formula that looks like this, and ultimately in this example come up with a variance on the sample of 2.99481. The variance is a measure of dispersion, but it suffers from the fact that it's computed from squared values. To eliminate this squaring effect, we compute a new measure of dispersion, which is frequently used. It's called the standard deviation. And all we have to do here is take the square root of the variance. So for a true standard deviation, you typically see the sigma being used here. You just take the square root of the variance. For a sample, we could use S instead of the sigma. Take the square root of the variance again, you get the sample. So you see the sample standard deviation there. In Excel, we could use a function to take the square root. It's just the SQRT function for the square root. So if we wanted, for example, the standard deviation on a true population, I would take the square root of the variance on the true population, and that would give me the standard deviation. Similarly here, SQRT function. So here we have the standard deviation on a sample, 1.87. Going forward, I plan to use the sigma to represent standard deviation, whether it's a true population or a sample. In actuality, it'll all be sample data that we're working with. So you'll see the sigma, which will represent the standard deviation on the sample data. Oftentimes, we refer to the standard deviation as volatility or vol. So why are both the mean and the standard deviation important in a risk sense? Well, you could imagine a little experiment. Here we've got 4 people, A, B, C, and D, and they're throwing darts at a dartboard. The goal is to hit the center of the dartboard. If you had A, and A manages to hit this center over and over again, we also have B, which has darts that kind of go all over the place here. C has darts that hit the same place, but not quite in the center. And then we have D, where the darts are scattered. Which conclusions can we draw? Well, if you think about it, A and B have the same mean. A and C have the same variance or standard deviation. C and D have the same mean over here. C and D have the same mean. B and D have the same variance or standard deviation. If you think about how dispersed the darts are. Now imagine if you were standing underneath, which one would you want throwing the darts? Well, I guess you'd be okay with A or C, right? But you definitely wouldn't want to be there if B or D were throwing the darts. So different types of distributions. We really started talking about kind of the simplest type of distribution. This is a discrete and uniform distribution. By discrete, we mean that there are only a finite number of outcomes. You know, if you think back to the die, you had 6 possible outcomes. You couldn't roll a 1.5 or 2.5. By uniform, we mean that every possible outcome has the same probability. Each outcome had a probability of 1/6 in the case of a die. But in real life, distributions often don't have these characteristics. As an example, here we have a new random variable as the number of dots facing up when 2 fair die, a pair of dice, is thrown. There are a total of 11 things that can happen, and they don't all have the same probability. If you think about it, we have a possible outcome. You can't roll a 1 if you have 2 die, but you can roll a 2, a 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12. Each of these has a probability associated with it, right? So there are different combinations that can get you to these different outcomes. would the probability distribution and the cumulative probability distribution on this look like? Well, the probability distribution would look something like this. Now, this is a discrete probability distribution because, again, you know exactly what the potential outcomes are. You can't roll a 5.5, for example. But you can see that the probability distribution function is not uniform. There are different probabilities associated with each of these different outcomes. In other words, it's greater to roll, you have a greater probability of rolling a 7 than you do a 3, for example. Any symmetric distribution has a mean, a median, and a mode in the center. Here, the mean, median, and mode are all 7. Here's the cumulative probability. Again, the cumulative probability is the probability that the value of a random variable will lie at or below each point. So you can see that at a value of 12, we have 100% cumulative probability. In other words, someone has to roll a 12 or less. The distribution that we just described for the 2 die is an example of a type of discrete distribution called a binomial distribution. It's discrete, but the outcomes do not have equal probability. We now consider distributions that are not discrete. These are said to be continuous. A random variable is said to be continuous if it can take on an infinite number of different values over some range of values. For example, the height of a child selected at random could have any value ranging from the height of the smallest child on Earth to the height of the tallest child on Earth. Suppose the shortest child is 15 inches and the tallest child is 70 inches. How many different heights are there between 15 and 70 inches if we measured with absolute precision? Well, the answer is an infinite. The simplest type of continuous distribution is the continuous uniform distribution. This distribution can take on any value between 2 values, A and B, and each possible value has exactly the same probability of occurring. You can see the PDF on a continuous uniform distribution, and the CDF would look like this. Built into Excel is a random number generator that generates observations on continuous uniform distributions having endpoint values of 0 and 1. The function is called rand. We will have uses for this function shortly. To use the rand function in Excel to generate a random number, from a continuous uniform distribution, we can just use the rand function with an open and closed parenthesis, and this will automatically generate a random number between 0 and 1. Now, to generate a different number, you can just hit F9 to force Excel to recalculate. Each time you hit F9, you'll see a new number appear, something between 0 and 1. You can keep hitting that and you'll see numbers generated at random. The random number generator built into Excel can be useful for all sorts of things. There are many types of continuous distributions, but the most common type is called a normal distribution, also called a Gaussian distribution. Normal distribution or Gaussian distribution has several important characteristics. It's continuous, it's symmetric, it can take on any value from negative infinity to positive infinity, and it's fully described by its mean and its standard deviation or variance. It's extremely well defined mathematically, and this will be useful for us when we try to determine risk measurement using normal distributions, confidence intervals, and ultimately try to calculate the value at risk. Looks like this for the probability density function. And of course, the cumulative probability would look like this. We often see this described mathematically like this. You can interpret this to mean that a random variable x is distributed normally and is normally distributed having a mean mu and a standard deviation sigma. Here we have two different normal distributions. X is distributed normally having a mean mu sub x, sigma sub x, standard deviation, and y is a random variable having a normal distribution with a mean mu y and a standard deviation sigma y. Let's see, these are coming from the two different normal distributions. Normal distributions have many nice mathematical properties. One of these is consistent confidence intervals. For example, we can expect that 90% of the observations drawn from a random variable that's known to have a normal distribution will fall within 1.645 standard deviations around the mean. Using these ideas, you can generate confidence intervals. Here, you could look up the z-score in a table. This is the z-score using a two-tailed test. So we could say that the confidence interval probability would be the mean, mu, plus or minus z times the standard deviation, where z can be looked up in a table, right? The z that corresponds to a 90% confidence interval using a two-tailed test is 1.645. For a 95% confidence interval, you'd be using 1.96, and so on. You can actually also use some built-in Excel functions rather than having to look up a statistics table in the back of a textbook or something like that. There's a function that we can use for a normal distribution. In Excel, the function is normSdist, and that will return the z that's appropriate for the confidence interval you're trying to generate. The only thing to be careful about is that when you use the normSdist function, it's going to bring it up for a one-tailed test since it's a cumulative function. So in other words, if I were to use the normSdist function in Excel and I plug in a z of 1.645, it'll give me 95% rather than 90% because it's looking only at one tail. So in other words, if you were looking for 90% confidence in a two-tailed test, there'd be 5% in this tail and 5% in this tail. But if it's only a one-tailed test, then the 90% would be a 95% on a one-tailed test because you're ignoring that other tail. Let me show you what I mean here in Excel. Here I would use the normSdist function, either this one. If you use this one, you have to use true for cumulative, or this one here, which is an older one. So let's say we go with normSdist, the newer version with the dots. To plug this in, I just type in whatever my z is. So if I plug in 1.645 and I write in here true for cumulative, you'll see it's giving me the result as a one-tailed test. 95% confidence is what it's giving me. Let's just say I use 1.96 here, and it's going to give me 97.5%. Right? This is the cumulative probability. this is of 1.645, and this one was 1.96. So these are just percentages. Just be careful, this is for a one-tailed test, since it's cumulative probability. So how can we use this? Well, the example here, we have a normally distributed random variable having a mean of 50 and a standard deviation of 10. If you wanted to know what's the 90% confidence interval on this two-tailed test, well, then you'd have to use the 1.645 z. And so you'd say, okay, take the mean, 50, plus or minus 1.645 times 10, the standard deviation. So you'd end up with confidence interval 33.55 and 66.45. So you can say with 90% certainty that the random variable will fall within this range here, between 33.55 and 66.45. So what does this have to do with risk management? Let's take a banking application. So suppose that JP Morgan's mean daily P&L, profit and loss, is $20 million, and that the standard deviation of its daily P&L is $80 million. Assuming that their daily P&L is normally distributed, what is the most money that JP Morgan might lose in one day at a 95% level of confidence? What we're actually asking here is for the bank's VAR, value at risk, for one day at a 95% level of confidence. More generally, VAR is defined as the maximum amount of loss that would be expected over a defined period of time. And that could be 1 day, 1 week, 1 month, a year. You would define this at a stated level of confidence. It could be 90%, 95%, 97.5%, 99%, etc. So you can denote this either VAR, 1 day, 95%. However, some people use the loss probability, so they would say the inverse, 1 day VAR, 1 day, 5%, meaning that only 5% of the time would we expect a loss greater than this value. So this can make things confusing, but most professional risk managers opt for the first method of defining VAR this way. And we'll talk much more about this later on in the course. So how can we figure this out? A 95% VAR is actually calculated from a 90% confidence interval, because confidence intervals are two-tailed, and VAR is only concerned with the lower tail, because really we're focusing on just the worst case. So what we'd have to do is use the 1.645z, and we would say, okay, take the mean, 20 million, minus 1.645 times the standard deviation, 80 million. And so VAR, negative 111.6 million. Most people would actually drop the negative sign, so they would say that the firm's VAR is $111.6 million, because VAR is understood to be a loss. We will have a lot more to say about VAR later in the course, so for now we'll just mention that it's become a very important risk metric in financial markets. But don't be fooled into thinking that VAR is always this simple to compute. So what's a standard normal distribution? Well, it's a very special normal distribution that has many applications. For now, it's important to know that a standard normal distribution always has a mean of 0 and a standard deviation of 1. Any non-standard normal distribution can be converted to a standard normal distribution using this equation here. So here, y is distributed normally with mean mu and standard deviation sigma. Z can be described this way. So we're basically converting an observation y from normal distribution over to z, which is a standard normal distribution. We can also go the other way, from a standard normal to a non-standard normal, having any mean and standard deviation that we'd like. For example, here, if you want to generate observations on a random variable denoted x, having a normal distribution with a mean mu, standard deviation sigma, we could use a program that generates observations on a standard normal distribution z, and then convert them from standard normal over to non-standard normal. This will all become useful later on when we do things like Monte Carlo simulation in a few weeks. Probability distribution associated with a random variable has certain key parameters that help to describe the distribution or departures from the suspected distribution, and these are called moments of the distribution. There are 4 moments. The first 2 are the mean and the variance, which we've already discussed. The other 2 moments are skewness and kurtosis. Skewness is the 3rd moment, kurtosis is the 4th moment. Skewness is a measure of symmetry. You can see here, this would be for a normal distribution, we have 0 skewness here. But if it's skewed to the right, we would say that's positive skewness. If it's skewed to the left, we would say it's negative skewness. Kurtosis is the 4th moment, and this is a measure of peakedness and tails. Here you can see we have normal tails. This one here, normal distribution with 5% of the distribution in each of the tails. So we would say that's mesokurtic. Data is consistent with a normal distribution. Here we have thin tails. There's less of the data in the tails than there should be. That's what we would refer to as platykurtic. So data is distributed heavily in the middle, in the mid-region here, thin tails. Here we have leptokurtosis, leptokurtic. This just means that data is heavily distributed in the tails, fat tails. So if you're looking at what appears to be a normal distribution, but you're not sure if it's truly normal, you could use kurtosis as one possible test of normality. So there are Excel functions that can be applied to a data set to solve for each of the moments. We've seen already the average function, as well as the variance and the standard deviation. But there's also a skewness function, it's the skew function, and kurt function for kurtosis. Skewness, a truly symmetric distribution would have no skew, so the skewness metric would come up 0. That's what we would see in Excel as well. Kurtosis, though, there's more than one common measure that's used for kurtosis. The textbook gives the formula for the original kurtosis measure. However, today, most people use a measure called excess kurtosis, which is really the original kurtosis metric less 3. And so you would see, if it's considered normal, you'd see a kurtosis of an excess kurtosis of 0, which is what we would see in Excel. It should turn up 0 for a normal distribution. Positive excess kurtosis would be fat tails, and negative excess kurtosis would indicate thin tails. So why does this matter in risk management? Well, suppose that you work in the risk management group of a financial institution and that you believe that your firm's daily P&L is normally distributed. Of course, that would imply that skewness and excess kurtosis are both 0. If this were true, you could rely on the mean and the variance to accurately compute a VAR. But what if you're wrong? What if the daily P&L is not normally distributed because there's skewness or excess kurtosis? For example, suppose that the lower tail of the distribution is excessively fat, and the upper tail is practically non-existent. That would indicate both skewness and kurtosis anomalies. What would happen if you simply computed the VAR in the usual way? Well, to make this concrete, let's assume that we again estimated the mean daily P&L at 20 million and the standard deviation of the daily P&L at 80 million. And let's go ahead and calculate the one-day VAR at 95% confidence. Here, we would assume a distribution that looks like this blue line here, a normal distribution. But in actuality, the true distribution looks more like this. We have a fat lower tail and a thin upper tail. Having incorrectly assumed normality, the VAR we reported is $111.6 million. But in fact, because the fat lower and the lower tail and the skewness, the probability of a loss greater than 111.6 million is far greater than 5%. So we significantly understated the VAR, and management can be expected to make bad decisions as a result of that. Note that this sort of skewed distribution with a fat lower tail is common for any company that writes a lot of options. The company collects a premium when they write the option, and they can't make more than that premium. But they have an unlimited potential payout if the underlying price moves against them, and therefore the P&L distribution has a very fat lower tail. Another type of distribution that's very important, particularly in financial markets, is the log normal distribution. These distributions are continuous, but they are not symmetric. They're strictly bounded at 0. They can't go below 0, but they can go to positive infinity. Notation-wise, the statistics literature depicts log normal distributions in several ways, but they all have the same meaning. So, you might see it like this, or like this, or like this. For example, here, R is a random variable distributed log normally with mean mu and variance sigma squared. Of course, the notation can be confusing because here we are referring to the natural log, not the common log. So we'll stick with this notation that we have here, as it is more commonly used. So the log normal distribution tends to look like this. This is the probability density function. Why are log normal distributions called log normal? Well, it's because a random variable has a log normal distribution if its natural log has a normal distribution. How can I get the mean and variance of a normal distribution from the known mean and variance of a log normal distribution? So here we are going from log normal to normal, and this is the way you would calculate this. So to solve for the mean on a normal from a known log normal, you'd plug it into this equation here, and to solve for the variance on a normal, taking that from the original log normal data set, you'd have to use this equation here. And so, of course, if you can convert a log normal to a normal distribution, you must also be able to convert a normal to a log normal. And so you would use these equations here to go from normal to log normal. So here's an exercise. Suppose variable w has a normal distribution with a mean of 5 and a standard deviation 2. What would the mean and standard deviation of e raised to w be? In other words, here we're going from normal to log normal, and then in the second part we'll go backward from log normal to normal. So first, let's focus on this first part here. We have this variable with a normal distribution. We want to convert it to log normal. We'd have to apply those equations to do that. So let's try it. So I'll put this in here. We'll just say from normal to log normal. Right? And so we have here a mean of, we said, 5 and a standard deviation of 2. So if we want to convert this over, we'd have to use the equation on the slides. which looked like this one here, going from normal to log normal. So we're going to use this equation here for the mean and this one here for the variance. So for the mean, we'd have to say it's equal to the function for e, the base of a natural log, is the exp function. So we'd be taking exp raised to the mean plus the standard deviation squared over 2. Let me just put this in parentheses here. So we end up with 1096.633. What about for the standard deviation? Well, of course, here we would have to use this equation here. Now, this actually gives me the variance. So later I would have to take the square root. So it's going to look like this. exp 2 times the mean plus the standard deviation squared, and then we will close this up here, subtract exp 2 times the mean plus standard deviation squared. So that's giving me this really big number, but that's actually the variance. What I would then have to do is take the square root of this whole thing so that I have the standard deviation, 8028.534. So sure enough, going back to this exercise, you can see that in the next part, we want to do the inverse. We want to go from log normal to normal, and you can see already what the answers look like, which corresponds to what we have in our Excel file. So we should be able to take from the log normal to the normal and end up with a mean of 5 and a standard deviation of 2. But let's try it. Of course, for this example, we would be using the formulas that look like this. So doing this, let's do this in Excel. So we'll say here, back to normal, the normal distribution. And so we'd be taking the natural log of the mean on the log normal minus 1/2 of the natural log of 1 plus the standard deviation squared over the mean squared. And I'm just going to put brackets around these just to be safe. So we should end up with 5. Right, sure enough, it looks like we've got 5. What about for the standard deviation? Well, here I take the natural log of 1 plus the log normal standard deviation squared divided by the mean squared. So here too, I'm getting a variance. I then have to take the standard deviation, square root of this, so that I have the standard deviation on the normal, which we know should be 2. You'll find in the homework that we'll have 2 data sets, each containing 1,000 observations on random variables, and you'll have to calculate things like the moments, the mean, the standard deviation, the skewness, and the excess kurtosis. And based on those, I'd like you to make a conclusion on the data sets, which one is a normal distribution, if either one is. You can also generate a histogram from each data set and see if it appears normal. In order to do that, in Excel, you will have to add in the data analysis toolpack. And then you'll see that within the data files there are columns labeled bin that you can use to draw the histogram. These are just preset intervals that you can see will be used nicely within the histograms. So Which kinds of random variables have log normal distributions? Well, things like future stock prices, commodity prices, future interest rates. Why would you suspect that these things have log normal distributions? Well, for one thing, they can't go below zero. Negative prices don't make sense. But there's no theoretical upper limit to a price, so they can go at least theoretically to positive infinity. Whenever logic dictates that a variable cannot go below zero but can go to positive infinity, you should suspect the possibility of a log normal distribution. Consider how future prices, like stock prices, might be modeled to obtain a confidence interval if we were dealing with a log normal distribution. Imagine that you're long this stock. More concretely, suppose that S is the future price of the stock at time t, we'll say 1 year from today, and S sub 0 is the price of the stock now. We know that the future stock price has a log normal distribution, so S sub 0 is a known value that can be thought of as a constant. Let's say it's $100. So you'd write this as this equation here. You'd say the future stock price is approximately log normally distributed, having a mean, mu sub s, and a standard deviation, sigma sub s. So let's suppose that the mean is $110 and the standard deviation is $15. And suppose that you want the 90% confidence interval and the 95% var for the time t price of the stock, future stock price. How would you get it? Well, since we need a confidence interval, you'd first have to convert your log normal to a normal, because normal distributions have nice standardized confidence intervals that we can work with and view. Since we know that the future stock price has a log normal distribution, we would have to use these formulas to convert the log normal to normal. So we'd end up, if you plug it all in, you end up with a mean and a standard deviation on the normal distribution. I would suggest you work through these and just make sure that you can get the right answers here. So once you have the mean and the standard deviation that has a normal distribution, you can then figure out the 90% confidence interval using a z of 1.645, since this is a two-tailed test. So we'd solve for the lower bound by taking the mean minus 1.645 times the standard deviation, giving us a lower bound here, and then an upper bound of the mean plus 1.645 times the standard deviation gives us an upper bound. The problem, though, is that this is actually not in terms of the price. This is actually in terms of the natural log of the price. So to get what we really want, which is 90% confidence interval and the var in terms of price, we have to undo the natural logarithm. And of course we can do that with the exp function, right? The base of a natural log. So if we just use that e to the power of the lower bound and e to the power of the upper bound, we now have the upper and lower bounds in prices. So we can conclude that with 90% confidence, the future stock price would be between $87.18 and $136.26. And the 95% var, when measured over this 1 year period, would actually be simply the lower bound, right? Because 95% var is the same as looking at a 90% confidence interval, since with the var we're just focusing on the lower tail. So here what we could do is we could say, well, in the worst case scenario, we'd have a price of $87.18, right? And that's with 95% confidence for the lower bound. So we just say $100 that we originally started with minus that lower bound gives us a loss of $12.82. Here to depict this, we have the 90% confidence interval. We have the prices. And you can see the 95% var is the value at risk, or how much we would lose with 95% confidence. And since it's just focusing on the one tail, 95%, z for 95% is the same as z for a 90% confidence interval, which focuses on two tails rather than one. What would be the 90% confidence interval if we had been short instead of long the stock? Well, realistically, the 90% confidence interval would be the same whether you were long or short the stock, but the VAR would be different if you were short. If you think about it, what would be the worst case scenario if you were short the stock? Well, if you're short the stock, you don't want the stock price to go up. So the upper bound would be your worst case scenario. And that amounted to a price of $136.26. Now, if you started with $100 for the stock price originally, then the VAR, the value at risk, would actually be $136.26 minus $100. So the value at risk, if you were short at 95% confidence, a 95% VAR, would be $36.26. Just one more point to make with respect to log normal and normal distributions. Suppose we want to work in percentage returns instead of dollar returns. How do you calculate a discrete return, denoted R? Well, suppose the current stock price is $100 and you don't know what the future stock price will be 1 year from today. However, you do know the mean is $110 and the standard deviation is $15. We could calculate the discrete return, otherwise known as a holding period return, by just doing this calculation here that you're used to. Take the ending stock price over the beginning stock price minus 1. That gives you a discrete return. If the future stock price turned out to be $120, you'd have a discrete return, R, of 20%, right? Simply taking 120 over 100 minus 1. If the stock price turned out to be $80, you'd have a discrete return of negative 20%, 80 over 100 minus 1. Right? Of course, another way to look at this, you've probably seen this, is taking the difference in price over the beginning price. That'll work as well. Now, thinking about a discrete return, what type of distribution does R have? Well, if you think about it, since S, the stock price, has a log normal distribution, if you divide ST by S0, you're essentially scaling the original distribution, but not changing it otherwise. So it still has a log normal distribution. And when you subtract 1, you wind up with a log normal distribution shifted left by 1. What would the mean of the distribution be? Well, you could see how that would be adjusted. And the standard deviation would be scaled as well. Just looking at this here. What would have happened if we measured the return using continuous compounding? To measure in terms of continuously compounded returns, you take the natural log of the ending price over the beginning price. What type of distribution does R have? Well, think about it. The reason a log normal distribution is called log normal is because its natural log is distributed normally. So when you measure returns continuously, you actually have a normal distribution. And this is one of the reasons why, really, in risk management and financial engineering, we often measure returns on a continuously compounded basis, because it tends to lend itself well to these normal probability distributions that have those nice mathematical properties we can work with. Of course, discrete returns don't possess those nice properties. What would be the mean of the continuous return? Well, really, you'd be looking at the equation to convert log normal to normal, and we'd have to add 1 because originally we subtracted 1 to arrive at the return. What would be the variance? Well, again, we'd have to use the equation that we saw earlier, adding 1 before employing this in the equation. So, for example, here, if we start with the mean and standard deviation of R, we can obtain the mean and standard deviation of lowercase r here. And then we're working with a normal distribution. And then we could go ahead and calculate the 90% confidence interval and a 95% VAR using a z here of 1.645 for the 90% confidence interval. And then for the VAR, in terms of a percent return rather than dollars, we have the lower bound, negative 13.72%. And we would typically drop the negative sign to display this as a positive, recognizing that it represents a loss. Right? If we want to convert the upper and lower bounds back to dollars, we would have to use the e, base of a natural log, raised to the rate, multiplied by S0. We end up with the same results that we used, when we did the original prices before. Something else that's nice about using continuous returns is that it's much easier to do everything in continuous returns and convert it back at the very end. It's nice because you can also convert from one time horizon to another. In other words, you can go from daily returns to annual, or monthly to annual, and back and forth. If you were taking a one-day mean, say here, 1 day, and you want to annualize it, you would simply multiply by t, where t is the number of days in a year. Or if it were monthly, a monthly mean, you'd take the monthly mean times 12 months in a year. Right, so typically we would use 12 for 12 months. For if it's quarterly, t would be 252 for daily, because there's 252 trading days in a year. But basically, yeah, so for the mean and the variance, it's a linear relationship, so you just multiply by t, number of days or number of periods in a year, the frequency. But for standard deviation, we would take the square root of t and multiply that by the periodic standard deviation. So for example, if it's daily, you'd multiply by 252 for the mean. If you're looking at the variance, you'd multiply by 252. But if you're looking at the standard deviation, you'd multiply by the square root of 252. And you'll see we'll be working with this often, so these are relationships that will become important later on when we discuss calculating the value at risk over different time horizons. I'd like to spend a little time in Excel practicing some of this. So if you can just download the data file that's appropriate for Module 2 that we're working on now, it's on our class website, and you'll see that we have 97 days of price data for a particular stock. What we want to do is calculate the continuously compounded daily returns, and then from that we'll convert these over to calculate the periodic mean and standard deviation, but then we will annualize those. So let's take a look at that. I've downloaded the Excel file from the class website, so it looks like this. I'm going to enable editing here. And you can see these are just closing prices from day 1 to day 97. So imagine here that time is marching forward. And so I'm going to calculate the daily continuously compounded returns using a natural log of the ending price over the beginning price. And so you can see that from day 1 to day 2, the stock price rose, and we end up with a continuously compounded daily return of about 0.21%. Now I'm going to fill this down. I'm going to copy it down, just double-clicking here on the autofill handle so that it populates all of the daily continuous returns. So what's the mean? Well, it's just an average. All right, just selecting the range of returns gives me an average daily return of negative 0.07%. What about the standard deviation? Here we can use the stdev function. stdev will work for a sample. Alternatively, you could use stdev.s, which also works from on a sample. And I'm selecting the values. Again, selecting that range getting a daily standard deviation of 0.017502. Now to annualize these, well, these are daily returns. So, the original data was daily data. So to convert this, I would simply take the mean times 252 trading days in a year. And that'll get me to the annualized mean. So typically, so here I'm getting a negative 16.96% average annual return. Even though the original data was daily, we often depict our results on an annualized basis. For the standard deviation, we would have to take the standard deviation on the daily data, multiply by the square root of 252. So we end up with an annualized equivalent of 0.2778. I'm going to convert this to a percentage as well, 27.78%. So we've worked through some examples here in Module 2. I'd like to just mention that you should take some time to review a statistics text and the class textbook to refamiliarize yourself with the following other types of distributions. Really, in this class, we'll be focusing more so on the log normal and the normal distribution, but of course it's useful to do a quick review on the other types of distributions as well.